Nope, nope, that wasn't it. Hi, so the name of the game today is taking all the things that we've been doing with the second derivative and the first derivative and putting them together to try to make graphs of these functions. We've been doing analytical means with this stuff, but can we do it graphically as well without the aid of a graphing calculator? So all of these are going to be approximate answers. They are not like the exact things, but I'm going to be trying to talk about like what are kind of the key things that you're looking to make as you create these graphs. So we have this problem from Finney. We need to find the absolute extrema of f and where they occur. So I'm going to start with that. So I know for something to be an extrema, the first derivative has to be either 0 or undefined. So I know that there's an extrema here where we're 0. There's also a potential extrema there where we're undefined. We also need to check the endpoints. So 0, 0, and 3, -2. So if we look at all of these, we've got a 0 right here. We could also use the second derivative test to know that this is a maximum for this one. And if we look at all of these numbers here, 2 is our largest number. So we do have an absolute maximum at 2, 1. We can use the fact that it's first derivative and the fact that looking at all of these numbers, we're not getting anything bigger because we found the derivative at all those, at the 2 points that matter and the 2 endpoints. If we're looking for an absolute minimum, it should be one of these things, whichever one has the smallest y value. So that's at -2, that endpoint. So that's that endpoint thing I was talking about earlier. Okay. Next, we want to find points of inflection. So the points of inflection are going to be where our second derivative equals 0 or is undefined. No, where it is 0. However, we only have ones on the endpoints here, so we don't have any points of inflection. You might be considering this part right here where it is undefined. That is potentially a point of inflection, but it has to pass that sign test. And if we hop over to our sign test at 2, we're concave down before 2 and we're concave down after 2. So that also eliminates that spot as a potential point of inflection. So now what we need to do is we need to take all of this information and graph our function. Now, since we have all of these f points, we can just plot all of those points. So we can plot 0, 0. I don't know why I'm using my mouse still. 0, 0, we can plot 1, 2. We can plot 2, 0. And we can also plot 3, -2 because they gave us all those points. They're very generous for that problem. Now, we also want to make sure that we have a maximum at 2 and a minimum at -2. But we don't want to just kind of go woo through that thing. We want to make sure that we meet the needs of what all these functions are doing. So if we look at that first derivative, at this point right here, we should not be able to differentiate right at 2. Something weird should happen. We also know we need to be concave down all the time. We should increase and then decrease in a concave down. So I can do that. That's easy. So I'm going to make this kind of dome there. However, at this point, I don't want it to curve nicely and stay concave down. I want it to be not differentiable. So I want to make like a sharp point right there. So I'm going to try to kind of come up and kind of do that. So where that's probably a little extreme. Let me see if I can try that a little bit better. So, but the idea is that this should not meet very nicely. If I look at that, I was like, ooh, that's a little gross. So it's not differentiable at that point because we didn't have a derivative right there. And there's our graph. You could make these shapes look slightly different, but that's kind of the general thing. Concave down, increasing, decreasing, concave down and decreasing, and this point should not meet very nicely. So we want to sketch a possible graph of our continuous function here. So our domain is from 0 to 6, and we want to graph f. We have the graph of f prime, but we want to make the graph of our original function. So they did give us a nice point. So I can graph at least one point. So I know it goes through 0, 2. So I know I have a point right there. Now, the diagram that we have, that is the graph of our derivative. So we know that f of x, we know we're going to increase here and here because that's where our derivative is positive. We're also going to be increasing on this interval. So from about, looks like about 5.5 and onwards, and then we're going to be decreasing on this interval and that interval because that is where the derivative is negative. We also know we're not differentiable at 4, so we're going to have one of those like kind of Kerr-Turkey points right there, so we need to make sure that it's sharp. And yeah, let's get some critical numbers. We have critical numbers where our derivative is equaling 0. So we should have critical numbers at x equaling 1 and 3 and about 5.5 approximately. And we can tell that this one is going to be positive then to negative by the first derivative test. We know that that is going to be increasing and then decreasing. That's going to be a maximum. We'll have a minimum right here. And then this one is going to be another minimum. So I know I should have a high point after at 1. So all I'm going to do is I'm just going to go up. I don't know exactly how high it's going to go. It could be here, it could be here, it could be there. We don't really know. So you just kind of pick one. So I'm not going to do anything too crazy. I'm just going to say it goes to about there. Then I know it should reach a minimum at 3. So I want it to go lower than it was before. So I have a minimum right there. This one also should be a minimum. So yeah, minimum. And then at 4, oh, that's actually a critical number as well. I didn't have that listed before because our derivative doesn't exist there. At 4, we should have, let's see, we are increasing and then decreasing, so that should be a maximum. So that should go up above this one. And then at about 5.5, we had another minimum. So we're going to just say we go down some. So we want to increase and then decrease. Now these first ones we want to be nice and curvy. So, oh, let me try again. These ones we want to be nice and curvy. However, after that we want to start being sharp about it. So, and then come up. So this can be more curvy, but this should be a sharp point at that spot. And again, these are approximations. You can make these taller or lower because we don't know all that much about the original function. We just kind of know the general shape of what it's supposed to do. I don't know how high that maximum is or how low those minimums are. I just can make estimates and compare them to each other. All right, next we've seen a graph like this back in Unit 4, but like trying to determine, okay, who's who? Who's the original function and who is the derivative? So we know that the original function should have the highest degree. So this one right here is a cubic. So that's got to be the original function. Also notice that we have a minimum at this point. So since that's a minimum, the first derivative should be 0. And we can see that this function is at 0 right there. Also, we have a maximum right here, and this, our first derivative, is also at 0. We also have a point of inflection of we're concave up in this region and then concave down in this region. So the second derivative should be 0 right here, and that's what this diagonal line is doing. We can also tell because it's a linear, and so that's 1 degree less than this quadratic. Okay, The graph of the first derivative of the function on the interval 7 to negative 5 is shown. Use the graph to answer the function. Where is f decreasing? So remember, this is the derivative, and we want to know where f is decreasing. So we don't want to know where the derivative is decreasing. We want to know when the original function is decreasing. And that's going to be where the derivative is negative. So between these 2 points. So let's see, this is negative 2. So that looks like to be about from negative 3 to 1, since that is where our derivative is negative. And when the intervals of the graph is it concave downward? So for f to be concave downward, that is where the derivative is decreasing. So that's what so where our derivative is decreasing. So we're decreasing on this interval right here. It seems to go to about negative 1 or so, approximately. We don't know for sure. It seems to be about negative 1 is where the derivative is decreasing. So from negative 7 to negative 1. We do use an open parentheses for concave downwards. Single points can't be included. And what x values does f have a relative extrema? So relative extrema are going to be where the derivative is equal to 0. So we have critical points here and here. So that's at 3 and 1. We aren't able to determine the exact coordinate of those points. So we just say, hey, at x equaling negative 3, we should have a local maximum. And at x equaling 1, there should be a local minimum. And we can tell that because our derivative is going from positive to negative. That creates a maximum. And we're going from negative to positive. That creates a minimum, decreasing to increasing. At what x values does the graph of x have a point of inflection? So our point of inflection should be where the derivative has a maximum or minimum, will create a point of inflection for the original function. Because where the second derivative is 0, that's where we have points of inflection. So we want to say, okay, well, when is the slope of this line being 0? So right there. So at x equaling negative 1, there's a point of inflection, since the graph of f prime has a local minimum right there. Oof. You can read all this. So the graph of the second derivative is shown. And so we want to try to figure out where f is concave upward or concave downward. So we are going to be concave up when our second derivative is positive. So where the second derivative is positive, right here, our original function is going to be concave upward. Excuse me. So from negative 2 to 6, we are concave upward, since the second derivative is positive. The original function is going to be concave downward wherever the second derivative is negative. So that's from negative infinity to negative 2, and from 6 to infinity. We don't have any end bounds on this one. Okay. Now this question, part B, is really asking the same question that part A is, where it is concave down or concave up, is asking the same thing about where the first derivative is increasing or decreasing. So the graph of f prime is increasing on the intervals from negative 2 to 6, since f double prime is positive right here. And then it is decreasing on the intervals from negative infinity to negative 2 and 6 to infinity, is where f prime is negative, because this is telling us what the slope of the derivative is, because that's what the second derivative is. It's just the derivative of the derivative, so it is the slope of the derivative. Because you can always replace the word derivative with slope. The x value at which the graph has a point of inflection. So we should get points of inflection where the second derivative is 0 or where it's undefined. We have the potential to get them. So we have second derivative equaling 0 at these 2 points. So at negative 2 and 6, because we have a second derivative of 0. We don't know for sure if it's going to be a point of inflection, but we can tell based on this graph because we're going from negative to a positive and from a positive to a negative. If this had bounced off the graph, so like if they had come up and hit this and then gone right back down, then we would not have had a point of inflection there. All right, now finally, we're going to take a look at this, and I'm going to try to draw graphs of the original functions. Now, this is, again, going to be something that's a little kind of shaky. It doesn't have to be perfectly like this. So we have the first derivative here. If we wanted to draw the original function, I know that at -2, I should have a maximum or a minimum. That's a critical number there. I'm going from increasing to decreasing, so that should be a high point at -2. Oop, oop. So I should have a high point here at -2. I don't know exactly where it's going to be, but it should be high up. And then at 2, I should have a low point because the derivative is going from decreasing to increasing. So maybe like here. I could even put it up here. That'd be fine too. In fact, I will. Yeah, why don't I put it up here? That's fine. So the idea is that it's going from decreasing to increasing, so I should have a minimum there. So then if I were to draw that graph, I would just kind of go whoop, 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 and that'd be done. You could do that same thing down lower. You could stretch them out farther. So like this would be a fine one too. Whoop, whoop, whoop. Just based on the information that we're given, that's all we can really tell. We know we have a minimum and a maximum. If I wanted to draw the second derivative, same kind of thing happens. Where the function is decreasing and then it increases. So we should have a negative slope and then a positive slope. And it should hit a 0 right there where we have a minimum point. So it should be going straight through the origin. I know it has to be the origin because at 0, where f prime is 0, the second derivative should be 0. And it should be negative on this side because the original, the first derivative is negative. And then over here, the first derivative is increasing. So we should have a positive second derivative at that point. So it should be pretty much a straight line. But how tilty you want to make that line, I mean, we don't know exactly for sure how tilty the line is, but it should kind of follow a shape, kind of like that. Doesn't need to be super precise. And that's it. That's it for this stuff. It's just kind of taking all the ideas that we've been doing and mixing them all together and bouncing back and forth between first, second, and original function. Thanks for watching. Have a good day.